These are the answers to the AP Chemistry packet that covers topics 6.6 to 6.9. On this slide, you can see Unit 6 at a glance. Unit 6 is entitled Thermochemistry. In this video, we will take a look at topic 6.6, Introduction to Enthalpy of Reaction, topic 6.7, Bond Enthalpies, topic 6.8, Enthalpy of Formation, and topic 6.9, Hess's Law. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 6.6, Introduction to Enthalpy of Reaction. Here are some essential knowledge statements from the AP Chemistry course and exam description. The enthalpy change of a reaction gives the amount of heat energy released for negative values or absorbed for positive values by a chemical reaction at constant pressure. When the products of a reaction are at a different temperature than their surroundings, they exchange energy with the surroundings to reach thermal equilibrium. Thermal energy is transferred to the surroundings as the reactants convert to products in an exothermic reaction. On the other hand, thermal energy is transferred from the surroundings as the reactants convert to products in an endothermic reaction. The chemical potential energy of the products of a reaction is different from that of the reactants because of the breaking and forming of bonds. The energy difference results in a change in the kinetic energy of the particles, which manifests as a temperature change. Enthalpy versus internal energy. In a college chemistry course, students may learn about the difference between enthalpy, symbolized by the letter H, and internal energy, symbolized by the letter U. Distinctions between enthalpy and internal energy will not be assessed on the AP Chemistry exam. Most physical and chemical changes studied in chemistry take place at constant pressure. Under these conditions, the change in enthalpy, symbolized by delta H, is equal to the change in heat that occurs with respect to the system. If a process is classified as endothermic, heat flows from the surroundings into the system, and the sign of delta H is positive. On the other hand, if a process is classified as exothermic, heat flows from the system into the surroundings, and the sign of delta H is negative. Now, in an earlier video, when I was talking about topic 6.2, energy diagrams, I had mentioned the change in energy, but again, energy and enthalpy are used so interchangeably in chemistry that when I talk about the change in energy or the change in enthalpy for a process or a chemical reaction, I mean the same thing. So the change in energy is positive for an endothermic process, and the change in energy is negative for an exothermic process. Now, what you can see at the top of this slide is a balanced chemical equation. I'm going to use this particular chemical equation as an example to teach you about the concept of mole of reaction. So mole of reaction is a very important concept in chemistry that students need to understand. So what do we know about this particular chemical equation? Well, the delta H is negative 5,327 kilojoules per mole of reaction. So we know from the negative sign of delta H that this chemical equation represents a reaction that is classified as exothermic. Again, negative delta H, exothermic. C4H10 happens to be a substance known as butane. So when 2 moles of butane gas react with 13 moles of oxygen gas, O2, it produces 8 moles of carbon dioxide gas and 10 moles of water vapor. So we're looking at a balanced chemical equation for the combustion reaction for butane. Consider the information given in the equation shown above. The symbol delta H of reaction, again abbreviated RXN for reaction, that refers to the change in enthalpy, that is the change in heat, associated with the reaction represented by the equation shown above. The units of delta H of reaction are written as kJ, so kilojoules per mole of reaction. Now it's very important that you understand that kilojoules per mole of reaction is not the same as writing kilojoules per mole. The unit, mole of reaction, is abbreviated MOL subscript RXN, and this unit is defined in terms of the specific set of coefficients for a particular chemical equation. The following conversion factors can be written based on the information in the equation shown above. So we have 5,327 kilojoules of heat that are released for every 1 mole of reaction. There's no negative sign that I'm showing you in my conversion factor, but when I say the word released, I'm referring to the amount of energy that is released, but I don't need a negative sign if I'm just talking about the amount of energy as a magnitude. In this reaction, 2 moles of C4H10 gas are consumed for every 1 mole of reaction. 13 moles of oxygen gas, O2, are consumed for every 1 mole of reaction. 8 moles of carbon dioxide gas are produced for every 1 mole of reaction. 10 moles of water vapor are produced for every 1 mole of reaction. Now, we have an example problem in your packet. Now, as I go through this particular example problem from your packet, there are 3 things that I would like you to make connections between, and they are the following. First, your knowledge of stoichiometry. So back in Unit 4, in Topic 4.5, when you did stoichiometry calculations, you would often convert from grams of a substance into moles, or vice versa, converting from moles to grams using information on the periodic table. And if you were given a balanced chemical equation, then you would use the coefficients in that balanced chemical equation to set up conversion factors to convert from moles of one chemical into moles of another. So I'd like you to make connections between your knowledge of stoichiometry and this concept of mole of reaction, which I am introducing in this video. So 1 mole of reaction is related to each and every coefficient in a balanced chemical equation. And then the third thing I'd like you to make a connection to is in topic 6.6 in this video, it has to do with the concept of the enthalpy change for a reaction or for a process. So the change in enthalpy, the delta H, is connecting mole of reaction to the quantity of heat that is either absorbed or released during a chemical reaction or a process. Okay, here we go. A student is asked to determine the amount of heat that is released when 1.00 grams of butane, C4H10, undergoes complete combustion in the presence of excess oxygen according to the equation shown. Now it says on the previous page in your packet, but it's right here on the slide in this video. The following shows how conversion factors are used to perform this calculation. So because we're starting with grams, we're going to go from grams to moles of butane. And on the periodic table, if we add up the atomic masses for 4 carbons and 10 hydrogens, we get a molar mass of 58.12 for this substance. So my first conversion factor is converting from grams to moles using the molar mass. In my next conversion factor, I recognize that 2 moles of C4H10 are consumed for every 1 mole of reaction. And in my next conversion factor, I recognize that 5,327 kilojoules of heat are released for every 1 mole of reaction. Now, if you're confused about the negative sign in delta H and why I am not including a negative sign in my conversion factor, what I'm saying here is in this final conversion factor, the reason why a negative sign is not used with 5,327 kilojoules is because this value represents the magnitude or the amount of heat released, and it does not represent the change in enthalpy for the combustion reaction. So all I'm doing is calculating the amount of heat that is released. So when I start with 1 gram, I would divide by 58.12, then I would divide by 2 and multiply by 5,327, and my answer comes out in units of kilojoules. So 45.7 kilojoules of heat is released whenever 1.00 grams of butane, C4H10, undergoes complete combustion in excess oxygen according to this particular balanced chemical equation. All right, so now we come to question 1 of your packet. So question 1 says to use the information from the combustion reaction to answer the following questions. Part A, calculate the mass of C4H10 that is required to produce 125 kilojoules of heat in this reaction. Assume that O2 is present in an excess amount. Include units in your answer. So part A of this question is actually very straightforward because it's essentially a reversal of the sample problem that I just talked about. And what I mean when I say reversal is that instead of beginning with grams of C4H10 and then calculating the amount of heat released, in part A of number 1, we're starting with the amount of heat, 125 kilojoules, and we're converting into grams of C4H10. So as I reverse my steps compared to this sample problem that I was going over earlier, I'll just be flipping a lot of these conversion factors upside down in order to get the units to cancel out in the appropriate way. So by starting with 125 kilojoules, I know I'm going to put kilojoules on the bottom, and then I'm going to put 1 mole of reaction on the top. So I'm going to use this conversion factor, but just put 1 mole of reaction on the top and 5,327 kilojoules of heat on the bottom. Now in my next conversion factor, I'd like to convert from 1 mole of reaction into the amount of butane. In terms of moles, that would be 2 moles of C4H10 for every 1 mole of reaction. And now in my last step, because I'm trying to get to grams or the mass of C4H10, I'm going to use the molar mass in such a way that I have 1 mole of C4H10 on the bottom and 58.12 grams of butane, C4H10 on the top. So if I pick up my calculator and I go from left to right, it's going to be 125 divided by 5,327 times 2 times 58.12, and then my answer will be in units of grams. So on my calculator, I get 2.7276. I'm going to round this off to 3 significant figures because 125 kilojoules has 3 significant figures. So I'm going to round my answer off to 3 significant figures by saying 2.73. And again, that would be grams of C4H10. All right, let's take a look at part B of this question. Now, you may remember back in Unit 4, when you were doing stoichiometry calculations, that some experiments involve a limiting reactant and an excess reactant. So back in part A of this question, it said, assume that O2 is present in an excess amount. So we have some clues in part B that this is not about assuming an excess amount, but in fact, we have to determine the limiting reactant. So here are the clues. We are given both the grams of butane, C4H10, and we're also given grams of O2. So in fact, it's going to be 2 parallel calculations involving the grams of each reactant. And then it says in this question that a chemical reaction proceeds until one of the reactants is completely consumed. So this will be a limiting reactant problem, and to calculate the amount of heat that is released in this experiment, we're going to have to determine the limiting reactant. So the limiting reactant will be the one that produces a smaller amount of heat in our stoichiometry calculations. So first thing I'm going to do is convert from grams to moles. So we already know that for every 1 mole of C4H10, there's 58.12 grams. Then I'm going to go from moles of C4H10 into 1 mole of reaction. So for every 1 mole of reaction, there's 2 moles of C4H10. And then I will use the amount of heat from the delta H. So 5,327 kilojoules of heat is released for every 1 mole of reaction. When I pick up my calculator, from left to right, it's going to be 15.0 divided by 58.12 divided by 2 times 5,327, and my answer will be in kilojoules. I get 687 kilojoules of heat released. But I'm not done yet. I don't know if this is my final answer until I run the calculations starting with 45.0 grams of O2. Again, the limiting reactant is going to be the reactant that produces a smaller amount of heat in our stoichiometry calculation. So let me go from grams to moles. So for O2, 1 mole of O2 would be 32.00 grams. Now, using the concept of mole of reaction, I can see from the coefficients in the balanced chemical equation that for every 1 mole of reaction, there's 13 moles of O2. And again, based on the value of delta H, there's 5,327 kilojoules of heat released for every 1 mole of reaction. When I pick up my calculator and I go from left to right, it's going to be 45.0 divided by 32 divided by 13, and then times 5,327. My answer will be in kilojoules. And now I have two numbers. I have 687 kilojoules of heat released from the butane, and I have 576 kilojoules of heat released from the oxygen. And I'm going to go with the smaller amount, again, from the limiting reactant. So the limiting reactant in this experiment is the oxygen, the O2, because the calculations show that O2 leads to a smaller amount of heat released in the reaction. So the answer to part B, the amount of heat, is 576 kilojoules. And again, that came directly from the limiting reactant in my calculations. Now let's take a look at question 2 in this packet. Question 2 in this packet was adapted from free response question number 1, which appeared on the 2018 AP Chemistry exam. And you can see an address on this slide, free response questions, and scoring information from past AP Chemistry exams can be found by visiting the following website. Now let's take a look at question 2. A student performs an experiment to determine the value of the enthalpy change, the delta H for the reaction, for the oxidation-reduction reaction represented by the equation above. Part A. Determine the oxidation number of chlorine in the chemical formula NaOCl, which is known as sodium hypochlorite. Now, the information that you need to answer Part A was actually presented to you back in one of my earlier videos for Unit 4, for topics 4.7 and topic 4.9, in which I presented the rules for assigning oxidation numbers to elements in various chemical formulas. And so highlighted on this slide says that the oxidation number of a metal in group 1, such as sodium, would be +1 in compounds containing sodium. So the oxidation number of sodium is +1 in most ionic compounds. Now for oxygen, the oxidation number of oxygen is usually -2 in most ionic and molecular compounds. There are some exceptions to this rule, such as hydrogen peroxide, H2O2, or oxygen difluoride, OF2, but NaOCl is not such an exception. So we would expect the oxidation number of oxygen to be -2 in this compound. Now, as for the halogen, chlorine or bromine or iodine, normally the oxidation number of those halogens would be -1 in most binary ionic compounds. But it says in this particular rule that when atoms such as chlorine, bromine, and iodine are bonded with oxygen or fluorine, they will have a positive oxidation number. So we can expect the oxidation number of chlorine to be a positive number when bonded with oxygen. And that's what we have in this example. So we can assign an oxidation number of +1 for sodium, -2 for oxygen, and the sum of the oxidation numbers of all three elements would equal 0. So if we do that math, then the oxidation number of chlorine would be +1 in the compound NaOCl. So the correct answer to part A of this question is +1, the oxidation number of chlorine in sodium hypochlorite, NaOCl. Now, let's take a look at part B of this question. What we need to do in part B is to calculate the number of grams of this compound that are needed to prepare 100.00 milliliters of a 0.500 molar solution. So that means 0.500 moles of this compound per liter. First thing I'm going to do is convert from milliliters to liters. So there are 1,000 milliliters in 1 liter. And then I'm going to write the molarity as 0.500 moles of this compound for every 1 liter. If I use the periodic table to figure out the molar mass of Na2S2O3, when I do that math, I get a molar mass of 158.1. So there's 158.1 grams of this compound for every 1 mole. If I set up the calculations with these conversion factors, my answer should be the number of grams of this compound. So when I pick up my calculator and I go from left to right, it's going to be 100.00 divided by 1,000 times 0.5 and then times 158.1. I'm going to round off my answer to 3 significant figures based on the molarity. So since the molarity has 3 significant figures, my answer will be rounded to 3 significant figures. So 7.905 is what I got on my calculator. I'm going to round that off to 3 significant figures and say 7.91 grams. So that is my answer to part B. Now I will move on to part C of this question. It says, in the experiment, the student uses the solutions shown in the table below. So in our overall balanced chemical equation, we have 3 different reactants. They're all listed as aqueous solutions. And in this table, we can see that each of these solutions has the same concentration and the same volume. So what that really is telling us is that there's the same number of moles of each reactant used in this experiment. So in part C, it says, using the balanced equation for the oxidation reduction reaction and the information in the table above, determine which reactant is the limiting reactant. Justify your answer. So I can start with 5.00 milliliters and convert from milliliters to liters because molarity is moles per liter. So first I will divide by 1,000 because there's 1,000 milliliters in 1 liter. 0.500 is my molarity, so 0.500 moles per liter. And when I do this math, the number of moles of each reactant that I get is 0.00250, or in scientific notation, that would be 2.50 times 10 to the -3 moles. So now that I know that I have the same number of moles of each reactant, and I know what that value is, let's see what comes next to determine which reactant is the limiting reactant. So we know that the limiting reactant will produce the smallest amount of product in the stoichiometry calculation. And so what I'd like to do now is to review a concept that I had introduced earlier in this video, and that is the concept of the mole of reaction. So what we can do here in part C is actually use the concept of mole of reaction to determine the limiting reactant. Now we know that we have 3 different reactants. We know that we have the same number of moles of each reactant in this experiment. So what I can do is convert each reactant into mole of reaction and see what happens. So for the sodium thiosulfate, which is Na2S2O3, it's understood that there's a coefficient of 1 for that chemical. So for every 1 mole of reaction, there's 1 mole of sodium thiosulfate, Na2S2O3. That means I have 2.50 times 10 to the negative 3 mole of reaction. Now for the other reactants, which are sodium hypochlorite, NaOCl, and sodium hydroxide, NaOH, I have coefficients of 4 and 2. And it's going to be 1 mole of reaction for every, and I can look at the coefficient. So looking at these 3 calculations, I'm dividing by 1, dividing by 4, dividing by 2, because those are the coefficients that are connected to 1 mole of reaction. Hopefully from this math you can see that if I'm dividing by 1, dividing by 4, and dividing by 2, it's going to be the sodium hypochlorite, the NaOCl, because it has the largest value for its coefficient in this balanced chemical equation. It's going to be my limiting reactant because in my calculations it gives the smallest value for mole of reaction. So we're starting with the same number of moles of each reactant, and we get a smaller amount for mole of reaction coming from NaOCl because we're dividing by the largest coefficient, the largest number. All right, now that I've answered question C, or part C of question 2, let's move on to the thermochemistry experiment involving calorimetry. So it says here the solutions, these are all 3 of these solutions, originally at 20.0 degrees Celsius, and you can see that on the far left of this diagram, are combined in an insulated calorimeter. And as you can see from the graph and the diagram, the temperature of the reaction mixture increases to a higher value. And so part D, according to the graph, what is the temperature change of the reaction mixture? So they don't want the final temperature, they want the difference in temperature. So the highest temperature where it plateaus in this diagram is between 32 and 33 degrees Celsius. So my initial temperature is 20.0 from the graph, and my final temperature is halfway between 32 and 33. So final temperature is 32.5 degrees Celsius. That's a difference of 32.5 minus 20 is 12.5 degrees Celsius. So my answer to part D is 12.5 degrees Celsius, which I read from the graph. Now the temperature did increase in this experiment. So earlier in a previous video, I talked about how what happens is that the thermometer is normally considered to be part of the surroundings and not the system. So when the temperature increases during the course of a reaction in which aqueous solutions are combined, that means that heat is released from the system to the surroundings. So this reaction should be exothermic, and we're already anticipating that the sign of delta H for the reaction will be negative. All right, part E of this question involves a calorimetry calculation using Q equals M times C times delta T. So we're given the mass of the reaction mixture is 15.21 grams. Part I of letter E says calculate the magnitude of the heat energy, that's going to be Q, in joules that is released during the reaction. Assume that the specific heat of the reaction mixture, which is C in this equation, is 3.94 joules per gram degree Celsius, and that the heat absorbed by the calorimeter is negligible. So we can do Q equals M, the mass of the solution, times C, the specific heat of the reaction mixture, times delta T, which was from part D of this question. So 15.21 times 3.94 times 12.5. My units of grams and degrees Celsius cancel out, so my answer on my calculator will be in units of joules. So I get approximately 749 joules when I round this number off to 3 significant figures. Now, the 749 joules of heat is released, but that is the amount of heat. This is not delta H. This is simply the Q, the magnitude of heat energy in joules that is released during the reaction. So again, in part EI, they wanted the magnitude of heat that is released. This is not delta H for the reaction. Let's take a look at part II of letter E. Using the balanced equation for the oxidation-reduction reaction and your answer to part C, which was about the limiting reactant, calculate the value of the enthalpy change of the reaction. So now they want delta H in units of kilojoules per mole of reaction. Include the appropriate algebraic sign, so either positive or negative, with your answer. We know it's going to be an exothermic reaction because heat is released and the temperature of the surroundings increased. So we're expecting that the sign of delta H reaction should be negative, and the units are kilojoules per mole. We already have 749 joules of heat that is released. Let's divide by 1,000. So to go from joules to kilojoules, we divide by 1,000. There's 1,000 joules in 1 kilojoule. So we have 0.749 kilojoules, and we'll be dividing by the mole of reaction. So coming from the limiting reactant, which was NaOCl, we're going to take our number of kilojoules of heat and divide by the mole of reaction. So I've got a negative sign because it's an exothermic process. So negative 0.749 kilojoules of heat for every 6.25 times 10 to the negative 4 moles of reaction. And when I do that math, I get approximately negative 1,200 kilojoules per mole of reaction. And if you'd like to go with 3 significant figures, you'd have to write that in scientific notation. So the delta H for this reaction would be negative 1.20 times 10 to the third kilojoules per mole of reaction. On this next slide, I will show you the official AP Chemistry scoring guidelines from the 2018 exam, and you can see that 1 point is earned for correctly calculating the value for mole of reaction. So that is the 0.000625 mole of reaction, which came from the sodium hypochlorite, the NaOCl, the limiting reactant calculation from part C. And then 1 point is earned for a negative delta H of reaction that was obtained by dividing the calculated value of Q in part EI by the calculated value of mole of reaction from earlier. So we have negative 1.20 times 10 to the third kilojoules per mole of reaction. All right, let's move on to part F of this question. Now, as you read through parts F and G of this question, it's very important that you understand the difference between Q and delta H. So Q represents the amount of heat that is either absorbed or released in a particular experiment. And the units of Q are typically joules or kilojoules. Now, delta H, on the other hand, is the change in energy or the change in heat that is associated with a particular chemical reaction or a process. And the units of delta H are kilojoules per mole of reaction. Also, delta H, because it is a change, it normally has either a positive sign for endothermic processes or a negative sign for exothermic processes. Q, on the other hand, does not normally have a sign because it's simply the amount of heat. So Q, the amount of heat for a particular experiment, delta H, the change in energy associated with a chemical reaction or process. So again, really make sure you understand the difference between Q and delta H. All right, so here is part F. It says the student repeats the experiment, but this time doubling the volume of each of the reactants as shown in the table below. So earlier in a previous part of the experiment, the volume of each solution was 5.00 milliliters and the concentration was 0.500 moles per liter. So in this experiment, the concentration of each solution is still the same as it was before, but now we've doubled the volume of each reactant. So part F, do you predict that the magnitude of heat, Q, in joules released in the second experiment will be less than, equal to, or greater than the value calculated in part E, I? That was like 749 joules of heat released. Well, we are doubling all three of the reactants. So what does this do to the Q, or the amount of heat released? Doubling the volume of each reactant will double the number of moles of each reactant. Therefore, twice as much heat should be produced in the second experiment. So the magnitude of heat, Q, released in the second experiment should be greater than the value calculated in part EI. Remember that there is a difference between Q and delta H. Let's take a look at our answer to part G. So we've just doubled all of the reactants and we've doubled the amount of heat produced. So Q is the amount of heat, whereas delta H is the change in heat. So here is part G. Do you predict that the magnitude, that is the absolute value of the enthalpy change, delta H reaction, in units of kilojoules per mole of reaction, calculated from the results of the second experiment, will be less than, equal to, or greater than the value calculated in part EII? Justify your answer. So it's very tempting to say we're doubling the heat, we're doubling the delta H, but this is a ratio. As we calculated earlier, it's a ratio of the amount of heat released with the appropriate sign divided by the number of moles of reaction. And so in trial 2 here, with doubling all of the volumes of each reactant, we are doubling not only the amount of heat released, we're also doubling the number of moles of reaction. So in the second experiment, both the numerator and denominator in this ratio is going to be doubled. So the magnitude of delta H actually stays the same. So unlike part F, where the amount of heat was doubled, delta H reaction is a ratio of the heat released, which is Q, divided by the moles of reaction. And so because the amount of heat released and the value of mole of reaction should be doubled in the second experiment, that means that the ratio stays the same. The magnitude of delta H reaction for this trial 2 will be equal to the value calculated in part EII. So yes, we double the Q, the amount of heat, but no, we do not double the value of delta H. All right, so now we're going to move on to our new topic. This is topic 6.7, bond enthalpies. Here are some essential knowledge statements from the AP Chemistry course and exam description. During a chemical reaction, bonds are broken and or formed, and these events change the potential energy of the system. The average energy required to break all of the bonds in the reactant molecules can be estimated by adding up the average bond energies of all the bonds in the reactant molecules. Likewise, the average energy released in forming the bonds in the product molecules can be estimated. If the energy released is greater than the energy required, the reaction is exothermic. If the energy required is greater than the energy released, the reaction is endothermic. The terms bond enthalpy and bond energy are used interchangeably. The bond energy values found in reference tables represent average values, and this is because the energy required to break a particular bond can vary depending on the structure of the molecule in which the bond exists. Bond energy values are associated with substances in the gas phase, so not liquid, not solid. That way, when you see a bond energy value, you know that because we're talking about the gas phase, we can focus on just that bond within that molecule and not any intermolecular attractive forces between molecules that might be associated with substances in the liquid or the solid phase. These are all gas phase data points. All right, so this is question 3, and what I tried to do in question 3 is to review Unit 2 a little bit, topic 2.2, which was on intramolecular force and potential energy. So you may see a review of Unit 2 that's built into this question. So question 3 says, use the information in the table above to answer the following questions. So in the table, we have 2 bond enthalpy values. One is for the hydrogen-hydrogen single bond. That's 436 kilojoules per mole. And then the other is for the carbon-carbon single bond, and that's 348 kilojoules per mole. So part A, 436 kilojoules of energy is blank when 1 mole of HH bonds are broken. So remember that breaking attractive forces, breaking a chemical bond, is an endothermic process that absorbs energy. So 436 kilojoules of energy is absorbed when 1 mole of HH bonds are broken, and then the opposite is true when bonds are formed. So 436 kilojoules of energy is released when 1 mole of HH bonds are formed. So breaking is endothermic, forming is exothermic. Part B, do you predict that the bond energy of the iodine-iodine bond should be less than or greater than 436 kilojoules per mole, which is that of the hydrogen-hydrogen bond? Justify your answer. So to think about this particular question, you have to imagine periodic trends in atomic radius and decide if iodine is larger or smaller in size than hydrogen. This is a review of part of Unit 2. So topic 2.2 was on intramolecular force and potential energy. So here on this slide, we're comparing the bond length and the bond energy of chlorine and bromine. And the highlighted portion of this sentence on the slide says a shorter bond is harder to break and a longer bond is easier to break. So we can see that in the comparison of chlorine and bromine. So because bromine is larger in size than chlorine, the bond length between 2 bromine atoms is longer than that of chlorine, and the bond energy to break the bromine-bromine bond is less than that of chlorine. So now that we know that there's that relationship between the size of the atoms, the bond length, the bond energy, you should be able to recognize, based on their relative positions on the periodic table, that the iodine atoms are much larger in size than the hydrogen atoms. So we'd expect for 2 H atoms a shorter bond, which is harder to break, and a higher bond energy. And then for iodine, we'd expect, because the atoms are larger in size, a longer bond, which is easier to break and has lower bond energy. So the answer to part B is the following. The atomic radius of iodine is larger than the atomic radius of hydrogen. The bond length of the iodine-iodine bond is longer than the bond length of the hydrogen-hydrogen bond. And since a longer bond is easier to break than a shorter bond, we would predict that the bond energy of the iodine-iodine bond should be less than 436 kilojoules per mole. Now, in part C of this question, we're also going to review something that you learned in topic 2.2, intramolecular force and potential energy. And it says, in a covalent bond, the bond length is influenced by both the size of an atom's core, which we just talked about, and the bond order, single, double, triple. So as you go from single to double to triple, you increase the bond order and you increase the strength of the bond. So bond with a higher order are shorter and have larger bond energies. We would expect a double bond to be a little bit shorter and stronger than a single bond. So the carbon-carbon double bond is stronger than the carbon-carbon single bond, should require more energy to break. So the bond energy of the carbon-carbon double bond should be greater than 348 kilojoules per mole, which is that of the carbon-carbon single bond. All right, now let's move on to question 4. In question 4, we are given a chemical equation, and the question says, do you predict that the sign of delta H reaction for the reaction represented by the equation above should be positive or negative? Justify your answer. Now, in many chemical reactions, bonds are both broken and formed, and it can be very complicated. But in this particular chemical reaction, it's very simple. Only one thing is happening at the particle level. So once we realize what's happening, we can easily make a decision about whether the sign of delta H should be positive or negative. Remember that a positive delta H is associated with an endothermic reaction, and a negative delta H is associated with an exothermic reaction. Now, I'm not going to draw the official Lewis electron dot diagrams with all of the bonding and non-bonding electrons, but I'm just going to draw a basic skeleton to show the connectivity between the atoms. And so what I see for the reactant, N2O4, is the skeleton structure has a nitrogen bonded to a nitrogen, and then there are 2 oxygen atoms bonded to each nitrogen. That's N2O4. Now, on the other side of the equation, we have 2 molecules of NO2. And again, in this very simple skeleton structure, not the official Lewis electron dot diagram, I can see that each nitrogen atom would be bonded to 2 oxygen atoms. Hopefully, as you can see on this structural diagram for the reactants and the products, that the bond between the nitrogen atoms is broken during the course of this reaction. So breaking a chemical bond is an endothermic process. A positive delta H is associated with an endothermic reaction or process. So the answer to question 4 is the following. The sign of delta H reaction for this particular chemical reaction should be positive because this reaction involves the breaking of the bond between the nitrogen atoms in the N2O4 molecule. And since breaking a bond is an endothermic process, and the sign of delta H for an endothermic reaction should be positive, then we know the sign of delta H should be positive for this particular reaction. All right, so in general, when we are analyzing a chemical reaction and we're given a table of bond energy data, the bond energy data that we are given, along with a balanced chemical equation, can be used to calculate the value of delta H reaction for a chemical reaction. And so the equation that we're going to use, which is not listed on the AP Chemistry equations and constants sheet, but just something you have to know based on your understanding that breaking bonds is an endothermic process and forming bonds is an exothermic process. You would add up all of the energies associated with the bonds that are broken in the reactant molecules. You would add up all of the bond energies for the bonds that are formed in the product molecules, and it would be total amount, or the sum of the bond enthalpies of the bonds that are broken, minus, again, because that's an exothermic process, that's where that minus sign comes from, so minus all of the bond energies or enthalpies of the bonds that are formed. All right, we're going to see 2 examples here in your packet, question 5 and question 6, involving using this equation of the sum of the bonds that are broken minus the sum of the bonds that are formed. So here we have a balanced chemical equation in question 5, and it says use the bond energy values listed above to calculate the value of delta H for the reaction represented by the equation below. Now, depending on how the AP exam decides to ask this question, sometimes you are given more bond energy data than you actually need. So they might be asking you to draw the Lewis electron dot diagram, and you might have to choose, is it a single bond or a double bond or something like that. But here, in this particular question, in question 5, all of the bond energies that we are given are exactly what we need in this particular equation. So on the left, we have CH4, and a CH single bond has a bond enthalpy of 413 kilojoules per mole. So because we have 4 of them, 4 CH bonds are broken. That would be, the math involved is 413 times 4. And I'll just keep track of the calculations as we go. Now the oxygen molecule, O2, contains an OO double bond. And so that energy of breaking that bond in the O2 molecule is 498 kilojoules per mole. But we have 2 oxygen-oxygen double bonds that are going to be broken during this chemical reaction. So 498 times 2 is 996 kilojoules. Now, we also have bonds that are formed on the other side of the equation. So there's a carbon dioxide molecule. 2 carbon-oxygen double bonds are formed. So I have 799 from the table, but that would be times 2. That's 1598. And then I have 2 water molecules, but in fact I have 4 OH bonds. So each water molecule contains 2 oxygen-hydrogen bonds, so I have a total of 4 of them. So 463 times 4 is 1852. So now what you're looking at is the total amount of energy can be calculated for the bonds broken, and the total amount of energy for the bonds that are formed can be calculated, and then you would do the sum of the bonds broken minus the sum of the bonds formed. So here's the math involved. 1652 plus 996 is equal to 2,648 kilojoules. That's the total energy absorbed when the bonds are broken. And then 1598 plus 1852 is 3,450. That is the total amount of energy released when the bonds are formed. So 2,648 minus 3,450. Now I'm estimating that the value of delta H for this reaction, based on the bond energy calculations, would be negative 802 kilojoules per mole of reaction. So that negative delta H tells me that overall this is an exothermic reaction, and the energy released when the bonds are formed was greater than the energy absorbed when the bonds were broken. Okay, let's go ahead and look at number 6 in the packet, which is very similar to number 5. We have a table of bond enthalpy data, and I can tell you in this particular problem, you do have some bond energy data that you don't need to use. So unlike the last problem, you actually have more information in this table than you actually need. It's very important to sketch the Lewis diagram for each of these molecules. So NH3 looks like this, with 3 NH single bonds and a lone pair of electrons on the central nitrogen atom, and that gives you the connectivity between the atoms for NH3. For N2H4, when you sketch that molecule, it's going to have a nitrogen bonded to a nitrogen with a single bond, and then there are a total of 4 nitrogen-hydrogen single bonds as well. On the other side of the equation, you may have to sketch out the Lewis electron diagram for nitrogen to double check if that's a single or double or triple, because all 3 of those bonds are listed in the table, but the correct answer for the N2 molecule is it's going to be a triple bond. And that's based on your understanding of Lewis electron dot diagrams. So we have an NN triple bond in the molecule N2, and then we have H bonded to H as a single bond. Now, what's missing on this particular slide, after I've drawn all of the Lewis electron dot diagrams for these 4 substances, is I want to make sure I have a good visual for how many molecules do I have to work with. And in this particular equation, the coefficients from left to right are 4, 1, 3, and 8. So I'm going to draw as many molecules as I need on both sides of the equation to get a really good picture of what bonds are being broken and what bonds are being formed. So there are 4 molecules of NH3. There's 1 molecule of N2H4. There's 3 molecules of molecular nitrogen, N2. And there's 8 molecules of molecular hydrogen, H2. Now that I've done that, let's go ahead and do the calculations for bonds broken minus bonds formed. Okay, here we go. So these are the bonds that are broken in the molecules of reactants, and then these are the bonds that are formed in the molecules of products. So from the table, there's 391 kilojoules per mole for a nitrogen-hydrogen bond. But if I add up all of them, and again, you can get a better picture when you draw these molecules out, as I've done on this slide, there are a total of 16 nitrogen-hydrogen bonds in the reactants that are broken. And then don't forget, there is a nitrogen-nitrogen single bond, which has a bond energy of 163 kilojoules per mole. So 391 for the NH bond times 16 plus 163 for the NN single bond. That's a grand total of 6,419 kilojoules of energy. That's the energy absorbed when all of the bonds in the reactants are broken. Now, onto the other side of the equation where bonds are formed. So the nitrogen-nitrogen double bond was not used in this calculation, but the nitrogen-nitrogen triple bond, which is 945 kilojoules per mole, we have 3 of them in the products that are being formed. So I do that math, 945 times 3, and then I have the HH bond between hydrogen, so 436, but I have 8 of them in the products that are formed. So 2,835 plus 3,488, that's a grand total of 6,323 kilojoules of energy that is released when all of the bonds are formed in the products. So now we do bonds broken minus bonds formed. So in this particular reaction, it's going to be 6,419 minus 6,323. That's a difference of positive 96 kilojoules per mole of reaction. Well, hopefully those calculations and how I set them up and showed you the structural formulas of different molecules to help you count all of the bonds that are broken and formed. Hopefully that makes sense. We're now moving on to our next topic in the packet. This is topic 6.8, enthalpy of formation. Here is an essential knowledge statement from the AP Chemistry course and exam description. It says tables of standard enthalpies of formation can be used to calculate the standard enthalpies of reactions, and we're given an equation that says delta H equals, and I'll talk about that little symbol, that degree symbol or that superscript 0 in just a moment, but the delta H, the change in enthalpy for a reaction, is equal to the sum of the enthalpy of formation for all of the products minus the sum of all of the enthalpy of formation for the reactants. And we'll see examples of how that works. So the quantity delta H reaction with that degree symbol or that superscript 0, what that represents is the standard enthalpy change, or the enthalpy change for a process occurring at standard conditions. So standard conditions are defined as 1 atmosphere for the gas pressure, 1 mole per liter for the concentration of a solution, and a temperature of 25 degrees Celsius. Now, when you see that degree symbol, that means standard conditions, and when you see the subscript F, that refers to the enthalpy of formation. So the standard enthalpy of formation is defined as the enthalpy change associated with the formation of 1 mole of a substance from its constituent elements in their standard states under standard conditions. All right, let's take a look at number 7 in the packet. We can talk about enthalpy of formation. Question 7 says, the standard enthalpy of formation for nitrogen monoxide gas, which has the symbol NO, is 90.3 kilojoules per mole. Based on this information, answer the following questions. Part A, write a balanced chemical equation for the formation of 1 mole of nitrogen monoxide gas from its constituent elements under standard conditions. So the elements that are involved in producing nitrogen monoxide are nitrogen gas and oxygen gas, and they combine together to produce nitrogen monoxide gas. So the symbol for nitrogen gas would be N2 because nitrogen is a diatomic element, And the symbol for oxygen gas is O2 because it is also a diatomic element. So on the right side of the equation, we have NO. So this equation is now written with all of the correct chemical formulas, but it's not balanced. And even though you could put a 2 as the coefficient for nitrogen monoxide on the right side of the equation, it does say that the balanced equation should show the formation of 1 mole of nitrogen monoxide. So we're not going to put a 2 in front of the NO, but we are going to have to balance this equation. So we're going to use fractional coefficients to balance this equation. So on the left side of the equation, we're going to put a 1/2 in front of the N2 and a 1/2 in front of the O2. So now this is the balanced chemical equation, and the delta H for this particular equation is based on the given information. For the standard enthalpy of formation, that would be 90.3 kilojoules per mole. So the delta H for this reaction is positive 90.3 kilojoules per mole of reaction. Now, as we transition from part A of this question to part B of this question, we're going to have to make a connection between the equation that was written in part A and the equation that was given in part B. So part B says determine the value of delta H in units of kilojoules per mole of reaction for the equation below. Include the appropriate algebraic sign, so plus or minus, of delta H with your answer. So how is the equation written in part A different than the equation written in part B? Well, if we look at the 1/2, we don't see a 1/2 as a coefficient for any of the substances in part B. So the first thing I'm going to do is take the equation from part A and multiply each coefficient by 2. So when I do that, I have N2 plus O2 produces 2NO. And since I doubled that particular equation by multiplying each and every coefficient by 2, then the value of delta H would also be doubled as well. So the delta H is connected to the coefficients. So if you double each and every coefficient, you also double the magnitude of delta H as well. So now I have positive 180.6 for this particular equation. And the difference between what I just wrote and what they gave me in part B is that it's reversed. It's in the opposite direction. So if I reverse the equation, I would have 2 moles of NO on the left, and I would have 1 mole of N2 and 1 mole of O2 on the right. When you reverse a chemical equation, you change whether something is endothermic to exothermic, or if it's exothermic, it becomes endothermic. So that's going to change the sign of delta H. So it was positive 180.6 kilojoules per mole of reaction. Now it is negative 180.6 kilojoules per mole of reaction. So in summary, 2 changes that were just made are when an equation is multiplied, where each and every coefficient is multiplied by a particular constant, then delta H is multiplied by that same constant. And if a chemical equation is flipped around or reversed, then the sign of delta H would be reversed as well. So from the reaction in part A to the reaction in part B, it was multiplied by 2 and reversed. So 90.3 was multiplied by 2, and then the sign was changed to get the value for delta H for this new reaction. We're going to see a similar type of manipulation when we get to topic 6.9, which is Hess's law. So keep those changes in mind. That will come up later in the video. All right, this is question 8. Use the information above to answer the following questions. So in the table above, we have the standard enthalpy of formation in units of kilojoules per mole for liquid water as well as water vapor. In part A, how much energy is associated with the process of 36.032 grams of water changing from a gas to a liquid under standard conditions? So let's write a chemical equation for that process of water changing from a gas to a liquid. So it's going to be H2O gas or H2O water vapor on the left, and then liquid water on the right. Now the delta H for this process is unknown to us, but we do have access to the information in the table to figure this out. So the equation that was given in this section, delta H for a particular reaction or a process, is the sum of the enthalpy of formation for the products minus the enthalpy of formation for the reactants. So we know that the product in this case is liquid water. So that would be the delta H of formation for liquid water. And then the reactant is water vapor. So delta H of formation for the water vapor. So the number from the table for liquid water is negative 285.8, and that's kilojoules per mole. And the number for water vapor is negative 241.8, again, kilojoules per mole. So negative 285.8 minus negative 241.8, that works out to be negative 44, and that's kilojoules per mole. So what does this number, negative 44 kilojoules per mole, represent? Well, for this particular process as written, so changing from 1 mole of water vapor into 1 mole of liquid water, that's condensation, that's an exothermic process. So that's why the delta H is negative. So 44 kilojoules of energy is released when 1 mole of water vapor is converted into 1 mole of liquid water. 44 kilojoules of heat energy is released. This gets us closer to answering this question, but we're not quite done yet because we haven't addressed the specific amount of water that was mentioned here in part A. It said 36.032 grams of water. Let's see how many moles that is. So on the periodic table, we know that the molar mass of H2O can be calculated, and it's approximately 18. It's 18.016 grams per mole. So hopefully you can see that 36.032 grams of water is actually 2 moles of water. So what we have so far is that based on the information in the table, we know that 44 kilojoules of heat energy is released when 1 mole of water vapor is converted into 1 mole of liquid water. So if I multiply by 2, then when 2 moles of water vapor is converted into 2 moles of liquid water, then twice as much energy would be released. So the answer is not 44, but rather 88 kilojoules. So how much energy is associated with the process of 36.032 grams, or 2 moles of water, changing from a gas to a liquid? And the answer is 88 kilojoules of heat energy is associated with this process. The energy is released. So in part B, does the answer in part A, does this 88 kilojoules of energy represent heat that flows from the surroundings to the sample, or from the sample to the surroundings? So from the surroundings to the sample of water would be endothermic, and from the sample of water to the surroundings would be exothermic. So this is an exothermic process. Delta H is negative. Heat is released. So the answer is that heat flows from the sample of water to the surroundings. It's an exothermic process. Energy is released. All right, this is question 9. It says the standard enthalpy of formation for an element in its standard state is equal to, and then there's a blank. We have to fill in the blank with a particular number. So a formation reaction is generally written like this. We have the pure elements in their standard states on the left, and we have 1 mole of a compound on the right. So for example, we talked about the formation of nitrogen monoxide earlier. You also could have the formation of liquid water, the formation of ethanol, C2H5OH, or the formation of gaseous hydrogen chloride. In all of these examples, we see that these are balanced equations with pure elements in their standard states on the left, and then 1 mole of a compound on the right. So if I'm trying to form an element in its standard state, well then by definition that would be 0, because you can't form an element if you already have an element in its standard state. So by definition, the standard enthalpy of formation for an element in its standard state is 0. All right, this is question 10 from the packet. It says, using the table of standard enthalpies of formation above, calculate the value of delta H for the equation shown below. Include the appropriate algebraic sign of delta H, so plus or minus, and the correct units with your answer. Now you may notice that there are only 3 substances listed in this table, but there's actually 4 substances in this balanced chemical equation. Well, from the answer to number 9, which says that the standard enthalpy of formation for an element in its standard state is equal to 0, then you might realize that one of the chemicals in this balanced chemical equation is nitrogen gas. So by definition, the standard enthalpy of formation of a pure element in its standard state, such as nitrogen gas, is equal to 0. So that's why it's not listed in the table above. All right, so here is our equation for calculating the delta H for a reaction based on the standard enthalpy of formation. So it's the sum of the standard enthalpy of formation for all of the products minus the sum of all of the standard enthalpy of formation for the reactants. So let's take this one part at a time. So the first product I see is nitrogen gas, and we have 3 moles of that. So it would be 3 times what's going to turn out to be 0 anyway, but 3 times the standard enthalpy of formation for nitrogen gas plus 4 times the standard enthalpy of formation for water vapor. So those are all of my products. The nitrogen and the water vapor are my products. And then minus the reactants. So 2 times the standard enthalpy of formation for N2H4 plus the standard enthalpy of formation for N2O4. So again, products minus reactants. So these are my reactants, N2H4 and N2O4. So now I can plug in all of the information from the table and then do the math to calculate the delta H overall for this reaction. So starting with the nitrogen gas, that's going to be 0 by definition, which is why it's not listed in the table. For water vapor, it's listed as negative 241.8 kilojoules per mole. For N2H4, it's listed as 95.4 kilojoules per mole. And then for N2O4, it's listed as 9.2 kilojoules per mole. Now, be very careful. I was saying kilojoules per mole to remind you that this is all for 1 mole. Do not ignore the fact that we have coefficients in this equation, and we have to use the coefficients in part of our calculation. So the coefficient for N2H4 is 2. The coefficient for H2O, water vapor, is 4. And obviously for nitrogen it's 3, but it's going to be 3 times 0. So that's not going to change any of our math, our calculations there. So 3 times 0 is still 0, but I have a 4 that I have to multiply by the value for water. And I have a 2 I have to multiply by the value for N2H4. So now we're going to do the following math. Products minus reactants works out to be the following. We have negative 967.2 for the products, and we have 200 for the reactants. If we've done this math correctly, now we're going to do products minus reactants. It's negative 967.2 minus 200. So the answer on my calculator is negative 1167.2, and the units are kilojoules per mole of reaction. So the answer to number 10 is negative 1167.2 kilojoules per mole of reaction. So we got that by using the equation products minus reactants for standard enthalpy of formation data that was from this table. Now, question 11 is similar to question 10 in that we still have to use the formula products minus reactants, and we have standard enthalpy of formation data. But as you can see in the table, there's a question mark. So one of the substances that's listed in the table, we do not know the standard enthalpy of formation. That's for something called octane, H18 liquid. But unlike number 10, where we had to calculate the delta H for the overall reaction, in this problem, in number 11, we are given that the delta H for the overall reaction is negative 10,150 kilojoules per mole of reaction. So we know pretty much everything except the standard enthalpy of formation for octane, for liquid octane C8H18. Let's plug in everything we know and then solve for the one thing that we don't know. Okay, so the delta H is products minus reactants. So it's going to be 16 times the delta H of formation for CO2 gas, that's one of the products, plus 18 times the delta H of formation for water vapor. Again, that's one of the products. So the products are CO2 and H2O. We have coefficients of 16 for CO2 and 18 for water vapor. And then for the reactants, we have 2 times the delta H of formation for liquid octane, which again, we don't know that value, but we can figure it out. And then plus 25 times the standard enthalpy of formation for O2. But again, that's not listed because by definition, the standard enthalpy of formation for a pure element in its standard state, like O2, is equal to 0. So 25 times 0 is still 0. And again, the reactants are liquid octane and oxygen O2. All right, let's plug in everything we know and solve for the one thing that we don't know. So the delta H for the reaction overall is negative 10,150 kilojoules per mole of reaction. For CO2, the delta H of formation, the standard enthalpy of formation, is negative 393.5. And then for water vapor, the standard enthalpy of formation is negative 241.8. So those are all my products. And then for my reactants, since I don't know the standard enthalpy of formation for octane, I'm not going to put a number in there yet. It's like I'm solving for X or I'm solving for an unknown. So here's the math. Negative 10,150 is equal to the math of 16 times negative 393.5, and then plus 18 times negative 241.8. So when I did that math on my calculator, I got negative 10,648.4. So now it just becomes an algebra problem where I can solve for the unknown quantity. And so when I do this math, I get 2 times the standard enthalpy of formation for octane is equal to negative 498.4. That's not my final answer. I have to divide by 2 to get my final answer. So the final answer would be half of that. So the delta H of formation, the standard enthalpy of formation for liquid octane, is equal to negative 249.2 kilojoules per mole. So what I did was I used the formula products minus reactants. I plugged in all of my information for the standard enthalpy of formation and the delta H for the overall reaction, and then I solved for the unknown. In this case, it was the standard enthalpy of formation for liquid octane, which is negative 249.2 kilojoules per mole. Now let's take a look at our next topic. This is the last topic in Unit 6. This is topic 6.9, Hess's Law. Here are some essential knowledge statements from the AP Chemistry course and exam description. Many processes can be broken down into a series of steps. Each step in the series has its own energy change. Because total energy is conserved, first law of thermodynamics, and each individual reaction in a sequence transfers thermal energy to or from the surroundings, the net thermal energy transferred in the sequence will be equal to the sum of the thermal energy transfers in each of the steps. These thermal energy transfers are the result of potential energy changes among the species in the reaction sequence. Thus, at constant pressure, the enthalpy change of the overall process is equal to the sum of the enthalpy changes of the individual steps. The following are essential principles of Hess's law. When a reaction is reversed, the enthalpy change stays constant in magnitude but becomes reversed in mathematical sign. When a reaction is multiplied by a factor, C, the enthalpy change is multiplied by the same factor, C. When two or more reactions are added to obtain an overall reaction, the individual enthalpy changes of each reaction are added to obtain the net enthalpy of the overall reaction. So these three essential principles of Hess's law are summarized on the following slide. The modification and how the delta H for the reaction is affected. If the equation is reversed, the sign of delta H for the reaction is reversed. If the equation is multiplied by a constant, C, the delta H for the reaction is also multiplied by that constant, C. And if two or more equations are added together, producing a new overall equation, then the values of delta H for the reaction from each equation are added together to determine the value of delta H for the reaction for the new overall equation. Now, let's take a look at question 12 in your packet. So when you are solving a Hess's law problem, a very common strategy is to find specific chemical substances in the overall equation that are also in the original equations that you were given. Now, if a substance has the correct coefficient, but it's on the wrong side of the equation, then that original equation would have to be reversed. So, for example, there's supposed to be 1 mole of carbon monoxide on the left side of the equation. In the overall equation, there should be 1 mole of carbon monoxide on the left. So in equation 1, I see 1 mole of carbon dioxide, which is good as far as the coefficient is concerned, but it's on the wrong side of the equation. So equation 1 needs to be reversed so that I can make sure that that particular chemical is on the correct side of the equation. Now, if you see that you have the right location of a substance, but you have the wrong coefficient, then maybe the original equation needs to be multiplied by a particular constant. So, for example, I see that there should be 2 moles of hydrogen on the left in the overall equation. So in equation 2, I see 4 moles of hydrogen on the left. And then I see there's supposed to be 1 mole of methanol, CH3OH, on the right side of the equation. In the overall equation, there should be 1 mole of methanol on the right. And in equation 2, I see 2 moles of methanol on the right. So the problem is they're in the correct positions relative to reactants and products and left and right, but the coefficients are wrong. So equation number 2 should be multiplied by 1/2. So if each coefficient should be multiplied by 1/2, that will take care of that problem. Now, if you're wondering, what about the carbon or what about the oxygen that do not appear in the overall equation? Well, they will get canceled out, and I'll show you how that works when we get to that point. So it says here, now that we've answered part A and B, which is to reverse equation number 1 and multiply equation number 2 by 1/2, it says based on your answers to parts A and B, write the modified versions of equations 1 and 2 in the space below. Show the modified values of delta H next to each equation, and show how the equations can be added together to produce the equation shown above. So reversing equation number 1 means that now it's going to be carbon monoxide on the left, and then carbon plus 1/2 O2 on the right. So I flipped it around, and notice that I changed the sign of delta H. It was negative 110.5. It has the same magnitude, but a positive sign. So it's positive 110.5 kilojoules per mole of reaction. Now for equation 2, I'm not going to reverse it, but I am going to multiply each and every coefficient by 1/2. So instead of coefficients of 2, 4, 1, and 2 in the original equation, Now the coefficients are 1, 2, 1/2, and 1. So this takes care of that problem in terms of getting the proper coefficients. But because I multiplied each and every coefficient by 1/2, now my delta H has also been multiplied by 1/2. So it was negative 401.4 kilojoules per mole of reaction. Now it's going to be half that value. So it's negative 200.7 kilojoules per mole of reaction. So it says we've already shown the modified versions of the equations. Okay, so I've done that. Shown the modified values of delta H. Now I have to show how these equations can be added together to produce the overall equation. So what I'm doing now is I'm drawing a line underneath these modified equations. This is similar to what you have seen in Unit 5 with kinetics and reaction mechanisms, where you cross off certain chemicals that appear on opposite sides of the equation, like catalysts and intermediates. So we're going to cross off any chemicals that appear on opposite sides of the equation that are the exact same thing. So I see a carbon on the left and a carbon on the right, so I'm crossing those off. I see 1/2 oxygen on the left and 1/2 oxygen on the right, so I cross those off. And now when I add these two modified equations together, I get exactly what I was supposed to get, which is 1 mole of CO plus 2 moles of H2 produces 1 mole of CH3OH. Now when I add these two equations together, I am also going to add these modified delta H values together. So positive 110.5 plus negative 200.7 gives me a value of negative 90.2, and my units are kilojoules per mole of reaction. So in part D, they're just simply saying, what is the value of delta H for the overall reaction? So we know when we added the two modified delta H values together, we get negative 90.2 kilojoules per mole of reaction. All right, there should be another Hess's law problem coming up. All right, this is question 13. Now, this question does not seem like a Hess's law problem, but in fact, it is. It's just a little bit in disguise. So let's talk about how this can become a Hess's law problem. In question 13, it says the first ionization energy of an element is the energy required to remove an electron from a gaseous atom of the element, as shown in the general equation below. So in this general equation, we have a generic symbol for an element, which is X. So on the left side of the equation, we have an atom. And on the right side of the equation, we have a positive 1 ion. That indicates that an electron has been lost. And so the symbol E with that minus sign represents the electron that has been removed from a gaseous atom of that element. Now, the values for the first ionization energies for the elements located in period 3 are plotted on the graph shown above. So on the graph, we see ionization energy on the y-axis, and we see atomic number on the x-axis. So the data that we are given is for sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. These are elements that are located in period 3. On the basis of this information, do you predict that the equation shown below should be classified as endothermic or exothermic? Justify your answer. So as I said earlier, this is in fact a Hess's law problem, but it's a little bit in disguise. So how are we going to figure this out? Well, what I'm going to do first is make some lines on this diagram to get a rough estimate of the ionization energy for different elements. So the first element that I see on the left is sodium. And I can tell from my estimate on the y-axis that the ionization energy value in units of kilojoules per mole for sodium is approximately 500. Now, the aluminum is approximately 600. And the magnesium looks like it's a little bit between 700 and 800, so I just estimated around 750. These are very approximate estimations. And you don't have to be that exact to get this question right, because we're not calculating the actual value. We're just deciding if it's endothermic or exothermic. So the specific numbers that I'm using can be rough estimates or approximations. Okay. Now, because the reaction that I've just highlighted on this slide involves aluminum and magnesium, then really in the diagram above, I just need to focus on the data for magnesium and aluminum. So I'm not worried about sodium, but I am worried about magnesium and aluminum. So the value for ionization energy for magnesium is approximately 750. And the value for the ionization energy of aluminum, again from this diagram, is approximately 600. So based on that generic equation, that general equation for the ionization energy of an element, aluminum would start off as an atom. If you take an electron away from aluminum, then that would be 600 kilojoules per mole to do that. And then for magnesium, it's the same idea. You start with an atom of magnesium, you take away one electron from the atom to produce a positive one ion, and that would be 750 kilojoules per mole based on my rough estimate. So now this is the Hess's law part of this question, because what we have to do is combine these two ionization energy reactions in such a way that when we add them together, they will produce this overall equation that we were given. So remember, the things that you can do with Hess's law is you can multiply an equation by a particular constant. You can also reverse an equation. So which one of these equations, the aluminum equation or the magnesium equation, do you think should be reversed so that when they are added together, they will equal this overall equation? Well, aluminum as an atom is supposed to be on the left, and it already is in that aluminum equation. But the magnesium is supposed to be a +1 ion on the left. So that magnesium equation needs to be reversed so that when I add the two equations together, they will equal that particular overall equation that I was given. So what I mean by that is if I reverse the magnesium equation by changing it around, by switching it around, then when I add the equations together, they will equal the overall equation that I was given. Now, when you reverse an equation, you change the sign of your delta H, or in this case, the change in energy, the delta E. So I went from positive 750 to negative 750. And now when I add these two equations together, the electrons are on opposite sides, so they would cancel out. I have exactly the equation that I was looking for, and the delta E, the change in energy, would be 600 plus negative 750, which equals negative 150. So remember, the question was, is this an endothermic or an exothermic reaction? And the answer is, this reaction is exothermic. I'm going to try that one more time. I'm going to go ahead and see if I can analyze this one more time, and hopefully this will help you understand it. So let me go back to what I was given in the diagram. Focusing primarily on magnesium and aluminum, what I can see based on the y-axis, that's ionization energy, is that the ionization energy for magnesium is greater than the ionization energy for aluminum. In fact, it doesn't really even matter what numbers I use, as long as the number for magnesium is larger than the number for aluminum. So I could use 600 and 700, for example, and I'll still get this question correct. As long as the magnitude of the ionization energy for magnesium is larger than that of aluminum, then it's going to work out. So when I reverse the magnesium equation, I'm going to flip that sign from positive to negative. And then when I add a larger magnitude number that happens to be negative to a smaller magnitude number that happens to be positive, it's going to work out to be negative overall. So this reaction, the one that I was given in this question, is an exothermic reaction. So it's based on Hess's law, and hopefully you can see that we got a negative change in energy for the overall equation, which is why it is an exothermic process. All right, I'm going to move on to the next Hess's law question in this packet. This is question 14. This also happens to be the last question in the packet. So let's take a look. we're going to modify equation 1, equation 2, and equation 3 in such a way that we will have the overall equation that's given to us as the result. So I'm going to go ahead and look for similarities between substances in the overall equation and in the original equation. So the first chemical that I see in the overall equation is C2H4. So where do I find C2H4 in the equations above? Well, it looks like C2H4 is in equation 3. And it's on the wrong side of the equation. It's supposed to be on the left, but in equation 3 it's on the right. So equation 3 should be reversed. The next chemical that I'm going to focus on is CF4. That's because there's two different equations that contain fluorine F2. So I'm going to focus on, is there a chemical that only appears in one of the equations? So CF4 is supposed to be on the right, but it's supposed to have a coefficient of 2. So in equation 2, there is CF4 on the right side of the equation, so I'm not going to reverse it, but I'm going to have to take equation 2 and multiply each and every coefficient by 2. That way, I can get 2 moles of CF4 on the right side of the equation. And as far as the HF, in the overall equation, I would need there to be 4 moles of HF on the right side of the equation. So HF is found in equation 1, but unfortunately it's not got the right coefficient. So if I take equation 1 and I also multiply each and every coefficient by 2, then I will get 4 moles of HF on the right. So now I know what to do to each of these equations. I know how to modify them. So the next step is to go ahead and make those modifications. So I'm going to write the modified versions of equations 1 through 3, and then show the modified values of delta H so I can process it. Okay, so for equation 1, because it was multiplied by 2, now the coefficients are 2, 2, and 4. And since I multiplied the coefficients by 2, I also have to multiply the delta H by 2. So the delta H was negative 546.6, but now it's been doubled. It's negative 1093.2. The next equation, equation 2, is also going to be doubled, where each and every coefficient is going to be multiplied by 2. So in our next equation, equation 2, when I multiply it by 2, the coefficients are now 2, 4, and 2 because it's been doubled, and I go from negative 930 in the original equation. Now the delta H is doubled, so it's negative 1,860. For equation 3, because it has to be reversed, you can see that I have C2H4 is now on the left, and then I have 2 carbons and 2 hydrogens on the right, so I flipped it. So the delta H was positive 52.4, and now as you can see it's negative 52.4. So I changed the sign of delta H. So I'm now ready, so I've drawn a line under these 3 modified equations. I'm now ready to cross off anything that appears on opposite sides of the equation so I can get rid of them. So again, kind of like a catalyst or an intermediate, I'm crossing off any chemicals that appear identical on opposite sides of the equation. So I see 2H2, so 2 molecules of hydrogen on the left and 2 molecules of hydrogen on the right, so those are crossed off. I see 2 carbons on the left and 2 carbons on the right, so I get rid of those. And now when I bring everything down from those individual equations, I have C2H4 on the left. I have a total of 6 moles of fluorine on the left. And on the right, I have 2 moles of CF4 and 4 moles of HF. So everything in that overall equation is exactly where it should be. So all of these modifications did exactly what they were supposed to do. And for the delta H, for the overall reaction, I have to add these 3 values for the modified delta H values together. So it's going to be negative 1093.2 plus negative 1860 plus negative 52.4. And so when I do that math, I get negative 3005.6 for the delta H for the overall reaction. So again, you've seen several examples of Hess's law. Again, this was the last question in the packet. I hope that you found these answers and explanations helpful. This is the end of the video. Thanks for watching.